Good day, good afternoon, good morning, whatever time it is where you are around the world. This is Dr. Mohamed Nezami again with another video episode of my post layout auto performance verification using EM and simulation tools. We're continuing with the series of trying to illustrate how the concept of post layout performance evaluation using simulation tools for as an example, where I take as an example one of the KU band SATCOM low noise block down converters that I have already presented. This was presented in the if you recall, in one of my videos. You can refer back to this video. It's this video here. So you can refer back to this video. Now, this is my channel, my YouTube channel. I would urge you to please subscribe and hit like and all that good stuff. Now, last time we showed how we can go into Cadence and take an existing layout, okay, which was driven from schematics, okay, how we evaluated the performance of some of the microstrip filters that are critical for the performance of the system. So what we did is I took as an example this hairpin bandpass filter, the image rejection filter in the LMB, and the local oscillator bandpass filter. And these filters basically are connecting to some of the QFN mimic packages that I used. This is the mixer, and this one is the an amplifier to amplify the LO signal. And then I showed in the last video, which is this video here, you can refer back to that video. How do we basically export the layout from Cadence, Allegro, BCB, or ORCAD, if you might call it. So I go to export, and then I export it as an ODB++ to, I could have done the same thing with Gerber or the CAD packages, the MCAD DXF. But what I did, I wanted to retain the stack layer and the third dimension, 3D, preserve the 3D information of the board, so I can bring in all the vias and holes and all of that good stuff, so I can analyze it into an EM simulator. And as if you recall, now this is a 10 board layer board, so which I only exported the top pattern copper and the second layer, which was the ground layer, okay? And I exported it into ADS this time as an example. I will eventually, in the next sessions, we will go into the HFSS as an example. So I came in here, and this is the board imported into ADS. And basically what I do in there, I did it this way, is you go in and you go import, and you specify the type of file, which is an ODB++, okay? And I imported that file. So let me just highlight the copper here. So this is the same exact layout now, except it's in the, I went from Cadence here fully into ADS, okay? And so what I did last time is I chopped off the bandpass filter in here from the DC bias network that is for the LNA. This is a MISFIT, GasFet, MISFIT pHEMPT, device from NEC. And so this is the input and output. This is the last stage. It's a three-stage low noise amplifier that uses this device here from NEC. This is a nice device. It has a very super low noise figure of around 0.3 dB minimum, course, you won't get that. You'll due to when you add up all the other networks that come in, which is the bias and the input output matching. So what I did is I chopped off this piece here, and the way we chopped it off is I went in, like I showed you last time, is we go in and highlight this here, and then you can go into the tool of EM and cookie cutting, and what you could, oh, sorry, you highlight this first, and then you go into EM tools and cookie cutting, and you cut that basically. And this is what we have here. And we go in next is we go in and add all the ports to it and run the EM on it. So, and I did that. I showed that last time, and it's as if you let me just remind you of that. So not this, but the okay, and we show the performance of this filter basically. So today I'm gonna go. What I'm gonna do is I'm gonna go again, and let me just show you where that. Let's see. We did the same thing to the yellow filter as well. So we took the yellow filter itself and did that as well. See here. Okay, here's the yellow filter being chopped off, and we preserved all the vias and 3D information of this, and ran this, and we went ahead and analyzed how this filter behaves compared to the performance that I got in the from the microstrip bandpass filter synthesizer in the Genesis tools that I did, where that filter was designed. So basically, you take the artwork in here, and you do EM analysis on it when you import it into the ADS tool to try to see whether the information is preserved or not. So basically, okay. And that's critical because this board, we want to do that before this board is sent to fab layout so that we can avoid any issues. Because when you bring in this filter, you have to extend the input and output so that you can get, like, for instance, in this case, I had to put this filter, connect it to the last stage LNA, okay? And then I had to also add more copper work to get it into the QFN, the mixer in here. So this here, I wanted to make sure that now what impact did that to the filter. We want to make sure this filter is okay before we send out to fab, because once we do that, that's very expensive. So today, let's do something more. Now, next videos, hopefully I'll get to cover where you can actually do co-simulations, meaning you could actually chop parts of this design and then actually do simulations where you involve both the EM model of the copper and then the S parameter model or the large signal model in there. But right now, let's just stick to the fact that we're trying to verify that this board is okay. It was all the designs that came in from different team of the different members of the team have been designed correctly, because you might get this filter from one designer and then LNA from another designer. So now here I am. I want to take this before we send it to layout, BCB fapping and BCBA assembly. I want to make sure that I could run a quick check just to verify that nothing corrupted on the during the layout process, because the layout process, you know, the RF engineer sends his DXF patterns of the microstrip work or the strip work or whatever, and then the BCB librarian creates symbols for those, just like we did here. For instance, as you can see here, this is the front-end bandpass filter with a picture that I put in there just for illustration. And this is the LNA last stage. So what we do, we put this here as a symbol, but behind the symbol, this symbol points to a PCB footprint. That footprint was created based on a CAD file that was sent by the RF engineer. So now this PCB librarian, we want to make sure that nothing went wrong during that process. And once you do that, the PCB designer also, and in this case, I was the RF designer and the PCB designer for this client. The PCB designer comes in and adds all this copper pouring, all these vias, all these extensions to extend the signal, the transitions, the 90-degree bends, and so forth, minor 90-degree bends. We add all of these so that we can get the signal through and make a PCB out of it, and something might go wrong. So today, let's go further, illustrate one more example. So which is, I want to look at this radial stub type DC bias network on the LNA. So we have the transistor in here. This is the GasFet pHEMPT device. This is the output matching, and this is the input matching in here. But in addition to that, I had to get the DC voltage from the DC regulation section into the drain of this device. And so to do that, in the scale, let me just switch over to the schematics. As you can see here, here's the LNA device, the GasFet pHEMPT device. This is the input matching and bias network combined. This here is the matching, output matching, and this is the DC bias network. The DC bias network is basically what we want to do is, if you recall, let me just show you the principles of this. If you have an amplifier, an RF amplifier, okay, you usually do your matching, input-output matching, but you still have to get the DC to both the drain and the gate, negative voltage to the gate, and the positive voltage to the drain. And we want to do that in such a way that we do not disturb the input and output impedances, because we match the device first for the optimal situation that we're in. We're optimizing that device, for instance, for noise figure. And then later on, we add this network in here, okay? And this network in here, what it is basically, it's really an RF choke that would, for DC, from the DC source to the drain, it looks like it's just basically a straight connection, okay? But for the RF, it would look open, meaning that we want to put a network in here so that the impedance looking into the DC supply is open or high impedance. And the way to do this is, of course, if it's moderate frequencies where we can use inductors, like from Coilcraft inductors, some of the air-wound inductors, we pick an inductor like it's drawn in here so that the self-resonance frequency of that inductor is right at the operating frequency, so that the impedance is highest presented to the drain, while it's really DC-wise, it's 0 ohm, okay? And of course, in the higher frequencies, we really can't do that. And of course, we put a cap in here. We have to put a cap in here if it's microstrip, because as you know, a quarter wave, this line in here, this section in here, if you implement it in microstrip, this is a quarter wave section. And for a quarter wave, as you know, it's an impedance inverter, and I'll show you in a minute with the equations. I'm assuming that you all are familiar with that. A quarter wave transformer inverts the impedance. If the load is 0, the input impedance of the quarter wave section will be open. So, and that's what we're going to try to do here. We put a quarter wave, and then we put this capacitor in here so that RF-wise, this point here is short. If this point is short in here, at this point, back looking into the quarter wave transformer, the impedance is open. So therefore, we fulfill the desired situation where we want the impedance for RF to look open, but for the DC to be 0. And the same thing is done also for the gate as well, even though here they show a resistor, but usually, like in this case, it is here. Now, at moderate frequencies, we can do this easily with either inductors or a mix of inductors, capacitors, or quarter wave sections. But the point here that is short, this is very critical that we would want this point to be short across the operating band. And unfortunately now, this capacitor, if you look at the impedance of it, it really deteriorates over frequency. So therefore, we can't really get a broadband response where we can present short to the quarter wave DC bias T. A lot of people call this bias T line. So what we've turned to is something called radial open stubs. And now, again, what this does, really, we use radial stubs in conjunction with a quarter wave suction to pass the DC or insert the DC into the drain and into the gate. And the way this operates, I'll show you in a minute, is that we assume the following. A quarter wave radial stub, okay, it's the same as if it's just a regular rectangular open stub. The input of impedance of it, because it's open, is really short. So therefore, the effectiveness of this here is really the same as this cap, except it operates over a wider band. So therefore, if this is short in here, and this line is a quarter wavelength, this point here looking this way vertically, the impedance is high. It looks open to the RF signal. And all of the energy, of course, will go into the device. Likewise, on the drain side, same thing. We want all of the power to go into the load, and none of it will go into the radial stub. And that's basically in my design in here, I use the same thing. What I did is I use a radial stub with a quarter wave line, and I used an additional line in here. This line in here, it doesn't matter what you are loading it with this way here for right now, because this point here is short. This point here, because this is an open quarter wave at the Ku band frequency somewhere between 10 and 13 gigahertz, this is really short, and this is short. This suction is a quarter wavelength, and therefore this here is open, and it will not disturb the frequency response of the output matching network of the GasFet device. Now, so what we're going to do is we want to come back to ADS in the layout, and I want to see analyze this, make sure that this is really operating well. Before we do that, let me go further and just illustrate the principle of the quarter wave, just so that if we have students in here that need some refreshing. So basically what we have, let's start out with what I want to show is what happens when a quarter wavelength loaded by open or short in this case, because that's what we have. We have in here, basically, we have a quarter wavelength, this one here, that is loaded with an open, and I have another quarter wavelength, which is this radial stub in here that is loaded with an open. So I have two quarter wavelength sections, one loaded with a short, which means its input impedance will be high, open, and the other quarter wave transformer is this radial stub, which its load is open, so therefore its input impedance is short. So the overall in here is what we want to verify right now by cutting this section and doing analysis on it. Why we do this? I do this because this could be another designer that wrote this in. I want to make sure that the layout was done correctly, or check as a design reviewer, or I could do just for my own fulfillment if I'm the designer in this case, just to see what happens. So let's go back to this equation. So we have the input impedance of a transmission line is given by this equation here. We have the characteristic impedance multiplied by the ratio of the load plus the J or I, the complex number, the square root of -1, times this here, which is the tangent of beta L. The beta is the wave number, which is 2 pi over lambda. Now, as you know, if the time the length, if the length is a quarter wave length, and a quarter wave, of course, in the material, not in air, okay? So what happens to this BL in here, it will be 90 degrees. And as you know, tangent, which is a sine over cosine, it will become basically the sine of 90 degrees over the cosine of 90 degrees, which means this will be infinity. So therefore, you have to take the limit to solve this. And when you solve this, you basically drop this, and you end up with this ratio in here, which is basically the Z0 square over ZL. So if the input impedance is equal the characteristic impedance square over ZL, that means it's really an inverter, because if ZL is 0, this will be infinity, meaning the Zn will be open. But if this is short in here, I'm sorry, that's what I'm saying. If this is open in here, Z0 square over infinity, that's 0, and Zn will be 0. So if the load is open, the input impedance of this is short, and it is indicated in here in this equation. So the input impedance of a quarter wavelength section loaded in here, if the ZL is 0, it looks open. If it's shorted, it looks it's open. If it's open, it looks it's short. Okay, that's really then. And practically, you know, I grabbed this from various board examples that are available on the net. Now we do this, so we have this here is an example of the very same device that I have here, which is this device here, okay? This is available from Mauser and DigiKey, and they're very cheap devices. So, okay, so we have this device, and we have both input and output matching networks, but also we have two radial sections and two quarter wave line transmission lines with high impedance. By the way, the thing I forgot to tell you is that this here, this line, how do we decide on the width of this line? This line, usually, you would want it high impedance, meaning it's about 100 ohm, anywhere from 80 to 120, depending. So as long as you can make the width of this line, of course, this is 50. This is here, but in this case, this substrate in here is Rogers material with a height of 20. So the width of the 50 ohm line, this is a 50 ohm line in here, and you can see this is almost 1/3 of it. Okay, so this line in here is about somewhere between 10 to 15 mil. Usually, you want to keep this line so that it's narrow enough so that your impedance is somewhere between 80 to 120. At the same time, you want to make it wide enough to withstand the current that you're providing the drain with. And in this case, this device here, in that case, I biased it some for 20 milliamps, some for 10 milliamps, okay? So as you can see in here, these are the high impedance line, drone, quarter wave section, and the radial on both the gate side and the drain side. This is another example. You don't have to do it radial. You can do it just basically an open stub. So what you see here is that he zigzagged the quarter wave line, high impedance line, and he went into basically an open stub here that is straight stub, not radial stub. And I'll show you in a minute what the differences are. The differences are basically, just so that you can have an idea ahead of time, is that they found out that when you have a single stub like this, this only optimal at a single frequency, where this line is quarter wavelength. As you move upward or downward from that frequency, this will not be any more open stub. It will act something else, and you get less and less isolation between RF and DC. And so somebody figured, well, can we put many of these stubs in parallel so that we can get a broader effective open stub at various frequencies within a certain band? And that's what this radial stub is, really. You can see that the distance from the point it connects to the impedance line to the edge of the radial stub varies until you get to the middle, and symmetrical on that side too. So therefore, really, it's a bunch of planary distributed open stubs, and you end up with broader bandwidth. Okay. So let's get back to, so what we want to do again is I want to go in and just isolate this piece here in my ADS and do performance check on it. And that's what I did here. So let's take this guy here. Now I could do just cut it using a chopping with a rectangle, but this time around I'm going to do it a different way than I did for the filters in the past video. So I'm going to highlight this. I'm going to go to the EM tools and do a cookie cutting, and you get two choices. You can get a square or this one. And so in here, you get a preview, you get to preview that, and that's what this does, okay? But I really don't want to cut it like this. I want to extend it a little bit more. So what happens is, let's see, what I want to do, you could do it this way, or you could do it even as a square, okay? So what I want to do, I will do convex, and I don't want to do it, I want to do 20 mils. Okay, so I want to do this. So this one this way. So now we have, this is isolated now. So, and of course, you can see that this is, I've got all the stuff in here. So this is good, ready to go. So what I'm going to do, I'm going to do some cleaning up here, get rid of this, and put ports on it, and do a frequency sweep on it, okay? And then analyze it to see whether it really performs correctly or not. So I'm going to do the, so I did that previously. So let me just go to that straight. Okay, here we go. So what I did is I brought this in, and I want to analyze this. So I put in ports on it, okay? And here's a third port in here. And I want to see really what is the impedance, the performance of isolation between this point and that point, and this point and that point. And remember, now, basically, a lot of these cases, they would chop, this line is not there. They would chop at this point and provide the DC. Like the example I showed here, for instance, is you can see here, this is the bias resistor that comes from DC. They sold this resistor right to the radial stub. In my case, I put an additional line in there, okay? I put this line. So this line here, as you can see here, really this resistor in here, I could have put it here, right in here, because at this point, the radial stub provides short RF-wise at this point. So whatever you do beyond this point, it really doesn't matter. But in my case, because of certain issues that had to do with this design, I had to extend another line in here. And we can talk about that offline, why that was special for that case. So whether this point is fed here or here, it really doesn't matter at this point. And then what I did now is I said, okay, well, since I've got this distance in here is the same as this distance. That's a quarter wavelength from here to here. And this is about 100 ohm line, somewhere between 80 to 100. What I'm going to do, I'm going to copy this. I'm going to stick another radial stub. I copied this here, and I put another radial stub, okay? And then I got the same thing, except I put an effectively just this is a different impedance line, which is just an open stub. And I want to see the frequency response of all of these. And these, of course, so what I did, let's go to the RF Pro for this. So we're going to analyze all of these and look at them. So okay, so here's my design, and let me solidify the substrate. So this is the bottom copper is shown. Everything is fine. So what I'm going to do right now is I need to look at the frequency response from this point to that point. And from, of course, the insertion loss also, that's another criteria that we need to look at. But this is such a short line. If this was designed correctly, then we would not get any loss in here, okay? By the way, the LNA you might see here that I've used in here, there is a resistor on the output of this GasFet LNA in here. That resistor really is a stabilization resistor. And you can see it even in the example that I have in here. See this resistor in here? Now it's not present in here. This resistor for that specific device, when I designed it and when everybody else designed this, they usually end up with having to stabilize this LNA device so that it's unconditionally stable. over all the frequencies. They add this resistor in here, okay? And these are, you can go to Gonzalez's book and see the explanation of why you would need to do that. That's a very common practice. And sometimes some people put it on the input, but in my case, we put it on the output just because this is an LNA, and we don't want the, as you know, the noise figure gets impacted by anything that produces thermal resistance, thermal noise at the input side. So we put it at the output side. And some people put a capacitor in here so that they can actually control where this shows up. You know, some people say, I want to stabilize, it's stable over this part of the band, but this part of the band is not stable. So what they do is they sometimes bypass this with a capacitor so that it is only present at another frequency region, so that, because this reduces the gain a little bit, okay? All right, so let's go back to here. So what we have in here, so these are the ports. You can see that the ports in here are basically had been brought up, okay? And so I ran this, and here's the frequency response of these three different ones, different bias T's, you might want to call them, for the LNA. So this is what I have in my design, which I can't change now. It's already done, okay? And then I said, for the heck of it, for just fun, let's look at two more examples just to illustrate what happened if I use a double radial stubs. And what really happens when you have a single stub in here, okay, rectangular stub. Now, of course, the placement of the stubs right now is not exactly the same. So what happens is this quarter wave line in here will resonate at different frequencies, but very close within the same area. And that's what happened in this response that we're going to look at. So we're going to look at it, and hopefully it's saved. So let's look at that first one. Okay, the first one, let's look at the return loss. This is the return loss, very good. So it resonates 10.5 gigahertz, and that's what I wanted. And if we go from 1 to 2, of course, the response is also good. You get very little loss, okay? And it's all pass in here. And if you look at the output return loss, it's the same thing. So this is this. Now, let's look at the second one. And the second one, let's just see what ports were those. So got 1, 2, 3. This is 4, 5, and 6. Okay, so let's look at 4, 5, 6. So we're going to look at 4, 4. Now, this is the double, the double one. Okay, this is the double radial stops in here. And of course, this what this does is that it's going to resonate two frequencies at two different places, and therefore, really, it will broaden the bandwidth of this bias network. And that's what I already can see this, because when you go 1, 1, they didn't resonate at the same place. But if you altered the length, if you tuned it so that they're right on each other, you can see that really this one is much wider response, okay? And so if you go from 3 to 4, I mean from 1, 2, 3, 4 to 5, you can see that it's minimal loss as well, okay? Where if you go from 1 to 2, it's the same thing. So basically, really, the double stub is actually gives you a much broader bandwidth. But in some cases, but in my case, a single stub, radial stub, was good enough, okay? So let's get rid of these, and let's just look at the rectangular one. And the rectangular one that I have in here, which is this one here. And this one is 7, 8, and 9. Okay, so let's look at that. So we got 7 and 7. So we're going to look at this one here. You can see it resonated here. Now, compared to, of course, the placement of the stub was a little bit at a different place. So you can see they're comparable, but really this is wider than this, but it's not as wide as this one here, the double stub. Okay. So let's see. Now, another thing that you can see on this, you can illustrate, is you can really show, I don't know if the field, well, now the video is already taken a long time, so, but you can show this, you can show the electromagnetic field distribution on these three and end up with a nice movie of the E field helper. So that's, so again, now what happens, so go back to this design in here and so we say, okay, well, this is good now, good enough. Okay, so we checked, this is fine. We're happy with the performance. So this is another example, ladies and gentlemen, of using post layout on an existing PCB that we do. Okay, so I encourage you to look at the other videos and check the last video that I did on this. So next, I think what we will do is we could probably look at the now let's start introducing a co-simulation concept where we will introduce, basically include the effect of these passive components and make a symbol, an EM symbol out of this and use it into schematic-based simulations where we can engage the EM model along with the S parameter file model and even the large signal model or the S-based S parameter model for the active devices. Okay, so we'll see what happens on the next session. So until the next sessions, I would like to thank you. This is Dr. Mohamed Nezami again, thanking you for another session on the what we introduced on the post layout performance verification. And this is, we're still going through the verification of as an example, I'm taking this KU band SATCOM LMB as an example. Now, I know one thing I could show next time is this. We have the IF section. Okay, we have some ceramic filters that I use in the IF section. And that's these guys in here. These are ceramic filters for the IF frequencies and the L band. So let's look at the verify that this here, this network, where I take the IF signal from the mixer, okay, from the mixer into these IF dual band filters. These are two filters and they are 75 ohms filters. There's not 50. And the reason they were made by many circuits 75 is because a lot of the LMB IF ports are 75. In my case, it was 50. So what I'm going to do, but I added an LC section at the input of these to match them to 50 ohm. And some might say, why go through that hassle? Well, because that device is nice and I had to use it. So I figured I could do an L section match from 75 to 50 and use it because of its neat frequency and size, frequency response and the size. So now, if you have any, like I mentioned earlier, I'm on a freelance contract RF designer. You could send me if you want to outsource any RF design work, please let me know. You can reach me at this number here or this email. My rate is very reasonable rate. Unlike the expenses, I'm based in Jordan, Jerash City, Jordan. I go back and forth to the US. I have clients mostly in the US, so I could work with you transparently as if I'm right next door to you. So I work with your engineers on any part of your design that you would want to outsource to get rapid, quick development. And I could fly in during the testing or during any of the design critical reviews that you may have. So until next time, my friends, I wish you all the good time. Thank you very much and have a good day.